Professor Naresh Patwari is the last speaker of this session.
Thank you, Arnan, for having this meeting and having me here. I've always, enjoyed. Unfortunately, this time I'm not able to walk much, but always enjoyed my runs with Balaji whenever I came to IISc. So this time I missed it. But today I'm going to talk about some work that we did over past 10 years and trying to connect this story using various techniques. Okay. Let me define what xenonucleic acids are. So, if you have a nucleic acid in which you have ribose sugar, if you replace the ribose sugar with any other chemical entity, and that's called a xenonucleic acid. Okay, my group works on lots of things. Here are some keywords that I use for last 5 years or so, but you don't have to worry, I'm not going to bother with all of them. But one of the things that comes to mind, I mean, if I don't know much about structural biology, you read any of the textbooks like Leninger or the Lubert-Strier's biochemistry textbook, two things that come to your mind is that a protein folds, okay, and there is a landscape on which it folds, okay, and then there's a DNA which is genetic material which kind of stacks and coils, okay. So these are for a physical chemist, one could ask a question that why do proteins have the structure that they have, how they have evolved, and also why DNA stacks and coils, and what is the underlying physical picture, okay, that we have. So today I hope to answer this, I mean our attempts to answer this question, why DNA stacks and coils. Okay, the story started a while back. In 2008 I was visiting the group of Prof. Pavel Hobza, and he had just published this paper using molecular dynamic simulations. If you quench the dispersion or quench the stacking, a DNA would look like a ladder, okay, not an helical structure, but ladder with your Watson-Crick base pairing intact. Okay. One thing that I must also tell you is that I must apologize to people who have heard this talk before. Okay, I mean, I have given this talk, parts of these talks in several places, so yes, apologies to all of them, especially Sanjay who heard this talk 2 days back. Okay, so the question was that, of course he said that, so the way they did this simulation was, there is this, okay, sorry. So what they did is they quenched the signal depth, okay. By decreasing this van der Waals depth, that you come to only a electrostatic situation wherein the two strands will just come together and forms a ladder like situation, okay. But if you look at the DNA per se, there are three entities that have that make up this genetic material or general nucleic acids. There is a base, okay, genetically we have these 5 bases, and there is a sugar, ribose sugar, either ribose or deoxyribose depending on RNA or DNA, and there is a phosphate, okay. Now as a spectroscopist we asked one question, okay, if there is 2 vials or bottles of this DNA, one is in which there is a base stacking present and one in which base stacking is absent, how would one distinguish, okay, because essentially your Watson-Crick base pairing remains. So how would you want to differentiate the structures? And this is a question that is too big to bite and not chew. So we decided to bite only a small portion of it, and then we started looking up stacking interactions. What are the spectroscopic signatures one would have if there is just a stacking? Okay. Now Benzene Dimer of course is a classic example where there is experimentally nobody has observed stacking, but all theoreticians for the run of money have said that there is a equally energetic a stacked dimer which nobody has seen it, okay. It's been 30 years of, or maybe more than 30 years of search, but nobody has found it, okay. And then we conjectured that the reason why you don't see the stacked dimer is because benzene lacks dipole moment. Now of course, as an experimentalist I am very well aware of the fact that absence of evidence cannot be evidence for absence, but it is just a conjecture, and it's not us. There are people who have probably looked at it before, and one of them is this paper by Wolfgang Stahl in which he looked at 1,2-difluorobenzene and showed that it stacks. And what we have done here is it's just introduced dipole moment by adding 2 fluorine atoms. Now, one of the things about this paper is this, I think, is probably the first paper on pi stacking gas phase complexes, but nobody ever looks at it, because the word pi stacking is not there in either in the title or in the abstract or in the entire paper. So, it's been overlooked just because the keywords, I mean, nobody reads papers, so everybody is looking for keywords, and if you just type the keyword, this will never appear. So, that's what they say, when these editors go on road shows, they say you should use the right keywords. I think that's where we have to learn from it. Okay. Then we set out, okay, of course, this is a kind of after story. This paper was already there, of course, I also missed it until we did first piece of work, and I think Arunan pointed us to this paper at some point of time. So, we looked at 5 set of molecules, okay, phenylastenes and fluorophenylastenes and this propargyl benzene, and then looked at the dimers of this, okay. And then we asked what is the role of the dipole moment in aggregation of these. So, in all the cases, okay, for example, when you look at the phenylastine and look at the stretch, IR stretch or the acetylenic stretch, the monomer has this spectrum and the dimer has this spectrum. All I see, I am not going to analyze in big, all you see is a very small red shift of this, okay, by few wave numbers, about 3 or 4 wave numbers. And when you do computations, it turns out that the anti-parallel pi stack dimer is the energetically more stable, okay. And at that point of time, based on the energy and the appearance of the spectrum, we connected these two, and we did lot more of this, okay. This is for the propargyl benzene, okay. Even in this case, you see a small 4 wave number, small redshift of 4 wave numbers in the spectrum, and then you also have the anti-parallel pi stack structure, which is here, which is the most stable. And then we looked at 3 fluorobenzenes, 2, 3, 4 positions, and all of them give the same result. So, whenever you have a dimer, in all these cases, the anti-parallel pi stack dimer is more stable, and the IR spectrum shows very small or few wave numbers of redshift, okay. Now, in all these cases, we try to assign the spectrum to a more stable structure, but we needed some more physical model. So, what are the points that we observe that the IR spectrum of dimer shows a very small redshift, and computations tell us that the anti-parallel structure is more stable. So, we need a model that connected these two facts. Then we came up with a simple electrostatic model in which, let us suppose there are stacked dipole, and a stacked dipole could have 4 possible orientations: parallel, anti-parallel, and slipped parallel and slipped anti-parallel, okay. And we extracted this geometry from the ab initio calculation and refitted to a potential which looks like this, which is nothing but a harmonic potential with the electrostatic terms in it, and we re-optimized this potential, and we found that in the case of anti-parallel, the length of the dipole increases. So, there is a lengthening of this bond, and in the case of parallel, the bond shortens. But shortening and lengthening of the bonds are not vibrational frequencies. You need to evaluate the force constant, and when you evaluate the force constants with respect to the unperturbed non-interacting case, the force constant in the case of anti-parallel structure goes down slightly. You can see the force constant has gone down by a marginal amount, while in the case of parallel, you have the force constant which is going to be slightly larger. That means, if you see a small red shift, it should be an anti-parallel case, and if you see a small blue shift, it should be a parallel. So, in our case, since in all the cases we see there is a small red shift in our spectra, we could assign it to the anti-parallel structures. So, that is about stacking, how one could look at the stacking experimentally. Then we come back to this nucleobases, and when you come back to nucleobases, there is this guy called Eric Kuhl at Stanford. Eric Kuhl has said something very interesting, is that if you replace by normal canonical bases, adenine, guanine, thymine, etc., by simple aromatic organic compounds like fluorobenzenes or something, okay, the DNA polymerase still works, okay, and it is able to reproduce, it is able to produce your DNA, except the fact that the fidelity in the process is lost. That means you are going to propagate much more mismatches. So, Eric Kuhl says that the reason why you need Watson-Crick base pairing is not, it's just to maintain the fidelity in the process of passing on the genetic material. Okay. Now, the question that here is that it's, he calls it a DNA isoster. There is a shape recognition rather than hydrogen bond formation. In the case when polymerases are working on DNA, there is only a shape recognition, and this Watson-Crick base pairing makes it better, okay, in terms of its fidelity. Okay. Now, of course, if you look at these bases, they are all N-heterocyclic aromatic compounds, okay, and there is also a theory by Slobodevsky and Domke which says that photostability of these bases is actually the real reason for natural selection. This is because, you know, when you photoexcite them, there is a very short lifetime component that allows you to dissipate this photoexcitation, thereby minimizing the genetic disorders. Okay. But we had a slightly different question to ask. The question that we asked is, if you look at any of these rings, 5 of them, there are at least 2 nitrogen atoms in each ring. Okay. Now, we wanted to ask why 2 nitrogens. Okay. So, if you want 2, the reason, then we said that, okay, let us do this experiment. Take the simple molecules pyrazine, triazine and pyridine, vary the number of nitrogen atom of rings and look at the propensity to stack. Okay. Once again, what we did was, we looked at phenylalanine as a probe molecule because there is a vibrational probe of, and we already knew how pi stacking it would behave. So, we looked at mixed dimers, okay, of phenylalanine with pyridine, pyrazine and triazine, and what happens is that in the case of pyrazine and triazine, you get exclusively stacked structures, because you can see once again there is a small red shift, okay, that you do not, but additionally in the case of pyridine you get a CHN hydrogen bond complex. Okay. So, if you have a pyridine that is 1 nitrogen, then you have a propensity to form both pi stack complex as well as the hydrogen bonded complex, but you have 2 of them, by hydrogen bonding is eliminated. So, there is an improved proficiency for the stacking formation and killing the hydrogen bond formation. Now, if you want something very definitive, you do not want competing interactions. So, putting 2 or more nitrogens kills the competition with the nitrogen atom, and that could possibly be the reason why there are at least 2 nitrogen atoms in these rings. Of course, 3 makes it better, but I won't know why, I mean, I wouldn't want to go into why, you know, nature has selected only 2 of them, but 2 is the minimum required when you want to kill the competition with hydrogen bonding and only do the stacking. So, quickly summarizing this, okay, what we figured out is, if you have a dipole, it assists in pi stacking, and if you put a nitrogen atom, the propensity to pi stack increases, okay, and when you have 2 or more nitrogen atoms, it kills the competition of hydrogen bonding. Now, but the other part is, this is just about the base, the other part is with the sugar. Okay. Now, if you the natural selection is the ribose and deoxyribose, okay, and in few years back, okay, there is this Belgian group which came up with a structure of a nucleic acid in which the ribose was replaced with xylose, okay, and this is an NMR structure of xylo nucleic acid with 8 mer each. So, it's an orthogonal it's an orthogonal 5 to 3 prime strand. Now, what they have done is, xylonuclease is nothing but xylose is nothing but a 2 prime epimer of ribose, that means 3 prime epimer of ribose, in which means the stereochemistry at 3 position is inverted, okay, or the 1 is not the oxygen, but 1 is where the base is connected. Okay. So, where from the base you start connecting 1, that is 1, the second one and third one, at third one you just invert the stereochemistry. Then they find that this is the, now we knew this Powell-Hobbs's calculations, in which he says that by decreasing the dispersion one could, you know, go from a helix to a ladder. So, this was known. So, we thought that this xylonucleic acid is actually already in ladder. So, can we transform it back to helix by increasing the dispersion? So, what they had done is, they had decreased this to make it a helix to ladder. Now, we wanted to go the other way around. Now increase the dispersion to make it helical. So that's our conjecture. So increase the dispersion and induce the helicity. That was the question that we had in our mind, and then we did these calculations and we found, and for the sake of comparison, we took the same sequence ribose as well, double stranded ribose, and ran these calculations, and we figured out that okay, when we did this calculation by increasing the epsilon to 5 by a factor of 5, what we found was the ribose overwinds, okay, while azalose hardly changes its structure. Okay. So there is no apparent increase, apparent change in the geometry by increasing the dispersion or epsilon, the van der Waals force, van der Waals well depth. So it is just, so what we figured out that RNA, you can with RNA you can, or double strand RNA you can wind and unwind, but in the case of xylose it is not amenable to structural change. So it is kind of very rigid body. Okay. So it does not go helix to ladder. Now the reason we wanted to find out why this is the case. So we looked at how the sugar is disposed with respect to the structure, nucleic acid structure. In the case of xylose, what happens is the orientation of sugar is almost perpendicular to the plane of the base. So in which the O, the sugar O is pointing towards the plane of the base, and when you quickly do some atoms in calculations, you can figure out there is a lone pair pi interaction, what Alok would call it as a n to pi star interaction. Okay. But I would prefer to call lone pair pi because I do not want to get into any of this controversy. I am not going to look at what is orbital contribution. Okay. But the same structure in this ribose, that does not happen. So in the case of xylose, this interaction kind of locks the conformational flexibility that the xylose will, ribose has and xylose does not. Okay. Then we said, okay, is it only case of xylose or is there any other? So we looked at this 4. Okay, the last one should be SS. Okay. In this, we looked at the 4 possible stereoisomers at 2 and 3 positions: ribose, arabinose, xylose, and lexose. Okay, and then we looked at the same sequence of 29 mer, and we figured out that okay, these the top ones are your initial structures. Okay, very close to what bDNA has, and then you run a 100 nanosecond simulation. At the end of 100 nanosecond simulation, you will find that a ribose and arabinose maintain helicity while lexose and xylose do not maintain the helicity. Okay. Now you can see that at the end your ribose or RNA is still a helix, arabinose partially is an helix, and while as xylose and lexose are anything but helices. Okay. Now we figured out that by doing this simulation, it comes out that the helicity depends on the stereochemistry that you have in the sugar moiety. So, but this is just one, so we ran several trajectories. In each case, okay, you will see that RNA at the end of your trajectory will remain as a helix, and arabinose to some extent remains a helix. Actually, it is not a helix, but it is kind of a slightly unwound helix with a larger minor groove and major grooves. While in the case of xylose and lexose, they sample geometries that are all over the place. Okay, you can see that in the first case it is almost like a straight ladder, while in the first case you have almost like in a plasmid kind of DNA kind of a structure. So they are sampling structures that are structurally very different. So which means there is no persistent length available, persistence length with the RNA, lexose and xylose sugars. But what about the deoxy ones? So in deoxy you have only one stereo center. So the stereo center at in the case of the RNA or deoxy ribose is at 3' position, but the other possibility is at 2' position. Okay. So we ran again the simulations, and you will see the same length, and you will see over the 4 simulations that we had, 4 trajectories, the deoxy ribose always maintains helicity, while the deoxy xylose, once again sample structures that are all over the place. So there is a lot of conformational flexibility that is given by. Now if you want, the question that I want, if you want to make a helix, okay, for whatever reason, okay. It could be a natural selection or the machinery that biology has. If you want to have an helix, you better choose ribose, because ribose gives best helices, okay. Now for why do you want a helix is a different question, but if you want a helix, you have to choose a ribose sugar, and that gives the best helix. So let me conclude by saying that xylose does not undergo helix to ladder transition just because or ladder to helix transition, just because there is a interaction lock through lone pair pi interaction. And what we figured out, the configuration at the 3' position determines the helicity. If you change the configuration at 3' position, you could go from a helix to non-helical structures, okay. Ribose makes better helices, okay. Arabinose also makes helices, but they are not as good as the ribose ones. The ribose has the best helices, and these could have played a natural selection, but I am not going to bet my money on it. Okay, this work was started by, the pi stacking was started by many people. Right now, my group, many people have, this guy who does MD on RNA kind of contributed to this work. I've also had collaborations with Professor Konking and Anirban Hajra. The experiments, of course, were supported by these funding agencies, and thank you all for your time.
Thank you, Naresh. Yes. Nice talk, Naresh.
Thank you.
See, in the case of ribose, sugar puckering is something which will contribute to how it is going to turn the helix around. Sugar puckering.
Yeah, but that sugar pucker is determined by the stereochemistry.
Isn't there a similar kind of pseudo-rotation cycle for
xylose also has sugar pucker.
other sugars?
Yeah, they have analyzed the sugar.
I think you'll be able to find an answer to some of these questions if you looked at that.
Okay, see, one thing that I know is that, there is enough literature which says sugar puckers determines the structure, okay. Of course, one of the things is that if you go to aDNA, bDNA, zDNA, that's a sugar pucker, change in sugar pucker,
yes.
Okay. But bDNA is predominantly formed, that is in biology, that is what is predominantly seen with almost like more than 90% of the times. But what I am saying is that if we all started with bDNA structures here, okay, in each case, okay, the initial structure is very close to what the bDNA has. Now the question is that why should sugar pucker come that way? The sugar pucker is probably controlled by the stereochemistry. I will not take that.
Yes. Indeed.
So, indeed, and there is an important point that I wanted to make here is that if you make a 3' deoxy or a 2' deoxy, okay. A 2', it is better to be it is preferring to deoxy rather than the inversion. Okay, that's one of the things that we wanted to say, but I didn't get to make that statement.
Naresh, it's interesting. The structure for phenylacetylene pyridine is not quite antiparallel. It almost looks like difluoroacetylene dimer.
It is somewhat yes, somewhat Gauss configuration. Yeah.
Is that the quadrupole or what is the?
Because I think one can think of it is like something that has a weight at one end and brings it down. So one can the nitrogen has ability to interact more, so it comes down, while the other part of the ring, which is carbon rich, tries to move away. And one can
difluoroacetylene is similar. It's not quite antiparallel.
Yeah, it is not quite antiparallel. Yeah, but in all, see that antiparallel thing I only showed in the case of when you have looking
phenylacetylene,
at homodimers of phenylacetylenes. Yeah. Okay. But if they are not, they still try to minimize the dipole moment. Okay, that's what we have seen when you look at the final dipole moment.
Is the fluorobenzene crystal structure known, Guru?
Fluorobenzene crystal structure is known, but it is nothing like this.
Antiparallel?
It's
not antiparallel.
It's not. It's actually also. It's very haphazard.
Sanjay.
Yeah, Naresh, when you turn the epsilon on for the xylose stuff,
okay,
does the base pair distances go down? Or
they don't. Actually, very little.
So that's the reason why they don't coil, because
no, that's what the reason is that this lone pair pi.
The rigidity of the phosphate sugar thing.
No, it is not rigidity of phosphate. It is the rigidity comes with the fact that the oxygen on the sugar, xylose sugar, is interacting with the, it's pointed towards the next base, and that doesn't change over the, whatever you do, unless you make epsilon 0. When it's only electrostatic, it goes away. Okay.
So you mentioned that when you have one nitrogen atom in a ring, it was bound on the edge of the ring by the lone pair. When you have 2 or 3, that you might get a pi stacking arrangement.
No, in the case of one, you have pi stacking as well as the C. Though they are both 2 isomers. Okay.
Okay.
So all I'm saying is that if you want to be something definite, you don't want competition. So that's one way to kill the competition. I mean, that's our hypothesis. Okay.
Okay.
So I don't want hydrogen bonding as well as pi stacking. If I want pi stacking, I will take only pi stacking.
Yeah, continuing on the same thing. You see, you have one nitrogen, in which case you have the stacking as well as the
Hydrogen bond.
hydrogen bond. The second one is we have 2 nitrogens. Does it depend upon where the nitrogens are? In
Actually,
the ring?
no, it doesn't depend on where nitrogens are. Now we have done more experiments with 1,2-pyrazine, 1,3, all those isomers, and doesn't matter.
Because you hadn't shown that.
Yeah, I hadn't shown, but this is much newer data. But it tells us. I just wanted to tell that story, but that's what it is. It doesn't matter. And we looked at even 5-membered rings, so doesn't matter at all.
Any other question, anybody?
So, why are you interested in the non-helical nucleic acids?
Oh, no. Why am I? I'm not interested in non-helical nucleic acids at all. The question that I wanted to, as a physical chemist, I asked what makes helix. See, think of it like this: when a helicase comes and interacts with the double-stranded DNA, first thing that it does, it's open up.
Yeah.
So we were interested in terms of potentials. How does it do it? So we are selling this as a helicase mimics, something like that.
Right. So the helix is extremely important for how DNA can wind and unwind, get packed in chromatin, etc. and etc. But it is a ladder-like structure.
Yeah, that's the why nature has chosen ribose, because it can do all that. And if it was not ribose, it wouldn't have been doing that. That's and I'm giving the answer that's already known. Okay, in some sense, yes.
Maybe Naresh is looking at extraterrestrial life.
Yeah, right. I will look after I'm dead. I'm sure.
Okay, so let us thank Sanjay. It's Naresh once again.